for the day is Jose Cambranos, and he's talking about periodic strings at finite temperature.
Okay, thank you. Good afternoon. Well, thank you to a few people who are here for the last talk of the day. I promise I will be short. So the idea is to talk a little bit about the work that I have been doing with Joe Capusta and Tita Virbis Bash about well, the idea was to extend the finite temperature computations to non-local quantum field theories, and then what I'm gonna do is to say a couple of words about the model in which we have been working, that is the p-adic string model. Then I'm gonna say, well, I'm gonna talk about a couple of basic ideas and present some results and say a couple of words about the phenomenology that you can do with these models. So you can find many models in the literature that are non-local, and the idea was if you can define a finite temperature field theory there and how to compute it. And in particular we are going to focus on this model that is related with the tachyon phenomenology in some string theories. So the idea is that you have a kind of a standard potential, power law potential, and what is non-local is the kinetic term, that as you see you have the derivatives in the argument of this exponential operator. So if you plot the potential, for example, has this form that is not bounded, but the kinetic term is not non-standard, so you cannot know exactly what is going on. Well, what we are going to do is just the standard procedure. So we compactify the temporal. We go to imaginary time and we compactify the time with being the temperature the inverse of the radio, and then we just go to the Fourier space. And then first of all we compute the free energy partition function. So you have the Matsubara modes, and you are working just with a real scalar field. So the only difference is that instead of having the standard propagator, then you have this non-standard propagator. Another reason to work with this model is that as you see, the high momentum are suppressed, so you have a theory that in principle is going to have a better UV behavior. So then the free energy is related, as in the standard case, with the logarithmic of the determinant of the propagator. So the first two terms cancel, as in the standard case. Well, you choose this normalization, and then you can compute this free energy as in the standard case. So the question is that the first term cancels because well, this as you regularize the vacuum energy, and the second term also cancels in this case because the function, this f that you have here, in this case is analytical, what is completely different at what's happening in the standard case. So in this case what you get at zero order is that the contribution is exactly zero, and that's related with the fact that in this theory you don't have perturbative states. So the point now is to turn on the interaction and see what is the contribution that comes from this expression. So again, you have to plug here the non-standard propagator, and what you find is that it's proportional to the third Jacobi function, to this function key, and this function key has this property that is interesting. You can write it in this way, like a sum of Matsubara modes, each n level the Matsubara modes that are the standard Fermat modes, but also you can write it as a sum of inverse thermal modes that are labeled with another parameter and that are proportional to the argument is proportional to the inverse of the temperature in the opposite case. So in fact, you can write the partition function and find this relation that is funny because it's exactly what is predicted by string theory, where you find this thermal duality because you have this projection between the thermal modes and the winding modes of the string along the compactified time dimension. So in this case you have this reason, but in the case of the p-adic string model you don't have any reason, but in any case you get it, what is very surprising. So another question that I would like to mention is that the fact that you introduce that you have a non-zero contribution to the partition function implies that you are going to have also a contribution to the propagator, and then in this case when the temperature is non-zero and you take into account this contribution, what is going to happen is that you are going to introduce in general ghost states, thermal ghost. So in order to avoid that, what you can do is to introduce this counter term where the value of this gamma parameter has to be computed order by order. So for example, at first order has this expression to avoid this thermal ghost. If you do that, then also what you get is a contribution to the partition function and to the energy density. So in blue is plotted the energy density without the absolute value of the energy density without this counter term, and what's happened is that it's negative. But when you introduce this counter term, then you have a contribution that dominates at low temperatures and also has the opposite sign. So also it cures the negative value of the energy. And then what you can try to do with these models is to propose also models for inflation or dark energy. Well, these are results if you take into account that this model can be defined in several dimensions, usually in 10 dimensions instead of in 4. And then what you get are the results are qualitatively the same, but you get more complicated expressions, and in particular this vacuum energy value is suppressed by the ratio of the scale associated to these strings. Thank you. Over the Planck scale. So as I say, then you can try to propose models for explaining the present acceleration of the universe. And for example, what we are doing is just fit some observations. So these are a fit of this dark energy to the union catalog of supernovas. The standard lambda CDM does a very good fit, and what you can get with this model is a similar good fit. So if you, for example, plot here the amount of the abundance of dark matter that you need to fit this data with respect to a string scale, then you see when this string scale is high, you recover you cannot distinguish it from a vacuum energy, so you recover the standard lambda CDM result. And then when this string scale is comparable to 1 in terms of the standard temperature of the p-adic fluid, then what's happened is that you need less dark matter than in the standard case. And that's all what I wanted to say. So the idea is that we have extended these finite temperature computations to non-local field theories. So in particular, we have worked with this p-adic model, and we have started to do phenomenological studies. Thank you.
Any questions? What's the plan in the future?
Well, as I say, we have started to check these possibilities. So the point is that well, the results are okay, but you need to see what's happened with the structure formation and with CMB and these kind of things. So the idea is to check all this stuff and see if the observations prefer better this model or just a cosmological constant. That also can be provided by this, but then if you cannot distinguish, it doesn't make much sense. That's the project for the phenomenological approach. So there are other ideas for studying other theoretical models.
Okay, let's thank Jose again.
Thank you.